Hi students! So, we are 2 chapters done and we're on the third one. This is chapter 3, Measures of Central Tendency in our Psych 218 class, Analysis of Behavioral Data. Introduction to Statistics. So in this chapter, we continue with our statistics adventure. We have reviewed why we do statistics, what are statistical procedures, why we ask questions about people, what data we get, and now we've gathered up the data and we start describing the data in frequency distributions and graphs, measuring variables and collecting scores. Now we can start asking questions about, hey, what scores can we expect from people? Like, what's the average of the class? Or, hey, is there a middle score somewhere? Is that the same as the average? Can we pull up the average or pull the average down when somebody does really well or really badly in the class? So these are some of the questions that we ask when it comes to central tendency. And another word for central tendency is expected score. What do you expect? So it would be examples like, is there an expected temperature that people would get? And we'd know that after measuring enough people and go, oh yeah, we can expect people to have a normal body temperature, quote unquote normal, of 35 to 36 degrees. It's actually 36 and a half or so. In our classes, we have an average, and we talked about this in our virtual classes. In this class at Alexander College, it's about somewhere in the 60s range, low 60s. In another classes, it may be higher or lower. And so in this chapter, we will be exploring the ways we can measure central tendencies and get expected values, whatever it is. It could be how much money you spend per month. It could be how many hours you sleep per day in a week. It could be the amount of exercise you get or the amount of food you eat, and so on. So this is very practical, and statistics continues to be. So there are 6 learning outcomes in this chapter as well. And this time, as we go on to our future chapters, starting with this one, there's going to be more math involved because we're starting to ask questions about what do we expect and how far the data spreads. In our next 2 chapters, we will use some math for this. So here we go, 6 outcomes. One, we want to understand and describe the purpose of measuring central tendency. We want to then define and calculate the free measures. And the free measures are as follows. The mean, that is the average. I'll just put AVG here. The median, that's the middle score. And third, the mode, the most common score, or the most frequent score. Number 3, we want to describe how the mean is affected, how the mean can change once we start changing scores in a distribution. Again, in a class, you might hear somebody pulling up the average or pulling it down, and often that makes the class either very happy or happier or sadder, depending on what's happening. If there are students that do really well and pull up the average, and the class happens to be quote-unquote scaled, a higher average would make more people fail the class or have more people below average. The same can be said, by pulling down the average, by having people doing not as well or scoring lower scores. And there are other ways to change the mean as well, because the mean is calculated using math. It's a theoretical and mathematical score. Number 4, we want to describe the ways in which the measures of central tendency are right to use, appropriate to use. When do we use the mean? When do we use the median? When do we use the mode? So we're going to explore the ways that is appropriate for each measure and when we use each measure as well. Number 5, we want to describe how these 3 measures are related to each other. So again, you can calculate and find all three measures of central tendency in most distributions. Sometimes you can get a distribution that has no mode. Sometimes you can get a distribution that doesn't have an existing mean, although there is a value for it. And these values can change depending on their position relative to each other if the shape of the distribution changes. So for example, when a distribution is symmetrical and it has only one mode, then the mean, median, and mode are exactly the same, kind of like this. Here you would have the mean, median, and the mode in exactly the same position, right in the middle. And that's great. And that is for normal distribution, there's only one apparent measure of central tendency, or at least one value for all three. But for distributions that have a non-symmetrical shape that is skewed left or right, positively or negatively, the mean, median, mode would be in different spots or different positions, and we'll explore those positions and what those are. Finally, we'll be able to draw and interpret graphs of distributions that tell us, hey, where are the central tendency measures? Like, where's the mean, median, and mode? So those are our 6 outcomes. Again, I'm going to try to fit all this in an hour, if possible, but looking at the math that is involved in this and the work that we're going to do together in the video, we might split it up in the middle somewhere. So the first 3 learning outcomes first in our first hour, and the next 3 learning outcomes 4, 5, 6 in the next hour. But we'll see. So to review the tools you'll need, because we're including all the scores to figure out what's the expected score, we're going to need to add them up. So that's the first thing we're going to need, and the tool for that is sigma notation. And because we'll be calculating the average or the mean, and I'll be saying mean more and more and more because that's the word we use for average in statistical procedures. But we'll also be using other formulas to calculate the median. Mode is fairly easy. You just look for the most frequent score. But again, the order of operations like BEDMAS or PEDMAS is definitely a must here. Okay. And the chapter 2 tools we're going to need are going to be our frequency distribution stuff. So that includes our tables, graphs, and shapes. So again, if you're not familiar with those tools, particularly your math stuff, you can go back and review the math material, the basic math skills. And if you're not familiar with your frequency distribution, you can go back to chapter 2. Again, 2 places, your textbook and these videos or lecture slides. Again, our skills are cumulative, our chapters are cumulative, so the better you understand chapters 1 and 2 in this course, the easier time you'll have with chapter 3. Going backwards here. So first we define central tendency, and we've already covered this a bit. So to summarize, here are the points. Central tendency is a statistical measure. Again, you can have a central tendency for a population, like a population mean, or you can have a sample mean for a sample. Here, the word statistical means statistical procedures. And so what we're doing with these measures of central tendency is to summarize the data with a single score that tells you where the middle of a distribution is. Again, you could use any or all or some combination of the 3 methods, mean, median, and mode, but they come up as a single score for each measure. So why do we do this? As we have said before, and this point summarizes, we want to describe the most typical, the expected, the represented score of the entire group using one score. This would be like choosing a representative of the class to say, oh, what is the class like? Yes, you could choose the best person or the person who had the highest score, but that's not necessarily representing everybody. That's just the best person. It would give the best impression, but is not representation or representative of the group. More logically, you would choose someone that is somewhere in the middle. And that person could give a more quote-unquote rounded perspective of how easy or how hard the course is. Probably the person who scored lower would say the course is harder, and the person who scored higher would say the course is easier. Again, we want to find the most representative, and this is why we use central tendency. So here's the first math bit, and we can use each of these tables and actually calculate the measures of central tendency. And so what I'd like you to do, and I'm going to do this in full, but you can do as much or as little as you want. And our goal is simple. We want to find the center for each distribution. So let's call this distribution A, distribution B in the middle, and distribution C. To describe these distributions a bit, again, you can pause the video and start describing them. You can tell yourself about the shape of the distribution. Is it a symmetrical distribution, a skewed distribution? You can also talk about how many modes it has or how many peaks it has. Does it have just one peak, one most frequent score, or does it have more than one peak? So in this screen right now, we're just going to describe the shape. Well, this looks symmetrical. And it has one mode, unimodal. One. Here it's not symmetrical. If I put the middle right here, and you can think about what skewed this is. And because the tail is at the negative end, we call this negatively skewed. And if you're thinking of a different one, where the tail is at the right end, that would be positively skewed. Okay. Here in distribution C, you see two peaks. So another word for that is bimodal. Bi here meaning two modes. Okay. So yes, we can describe these distributions, and knowing about the shape of these distributions is going to help us. What we can also do is locate the center. So with distribution A, the symmetrical distribution, because it's symmetrical, it's pretty easy. We know what the middle is. We can do that just by looking at it. The middle here is 5. Cool. Done. Pretty easy, right? All right, so with distribution B and C, things can get a little harder. One of the first things we do, regardless of any distribution, is we can count the number of scores in that distribution. Here you can see a type of histogram. No, actually, this is a histogram. Yes, it is, because it's hitting the intervals, and we got real upper and lower limits. So one of the things you can see here is a type of histogram, and it's a block histogram because each one of these are actual values, like 1, 2, 3, 4, 5, 6, 7, 8. I'll remove the line. 9, 10, 11, 12, 13, 14, 15, 16. So it looks like there are 16 scores here. You can count this one in distribution B, see if it's the same. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. One more time. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Same shape. Yeah, we know it's 16, but I'm going to write all the scores. So a couple of things you can do to practice this right away. You can actually draw or write your frequency distribution. So here you got one. Again, got to go from highest to lowest. 8, 7, 6, 5, 4, 3, 2, 1. And so 9's got nothing. 1's got nothing. And then we see, oh, 8's got 1. Okay, 7's got 2. 6 got 3. 5 has 4. That's the mode. 4 has 3 scores. 3 has 2 scores. 2 has 1 score. And we can do the same for these other guys as well. I'm going to do it at the top here for distribution B, so it's a little easier. Again, 9, 8, 7, 6, 5, 4, 3, 2, 1. So 9 has 2 scores, 8 has 4. That's our mode. That's our most common score. 7 has 3 scores, 6 has 2, 5 has 1, and the other guys have 1. Okay, in C we can do the same as well. Okay, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then we can also count. Oh, 9 has 2, 8 has 4, 7 has 2, 6 has nothing, 5 has nothing, 4 has nothing, 3 has 2, 2 has 4, and 1 has 2. Okay, so you can see we can practice by writing this frequency distribution tables already with these, right? And you can also figure out the total scores or the total X score values. So here what we do is we can do something like this. X times F. Okay, but for now we're going to do this for distribution B. So for B, if you draw a line right down the middle of the score distribution, you might think, oh, okay, the middle score might be either 5 or 6, but there are several ways to calculate this, and I'm going to come back to this table, and once we figure out the formulas, you can actually, or if you already know how to do it, you can figure out the mean, median, and mode. With mode it's fairly easy. We know for distribution A it's all 5, so that's great. For distribution B, we can calculate the mean. The median we can also calculate by ranking the scores from highest to lowest and counting the middle score. And that changes depending on if you have a even number of scores or an odd number of scores. We'll talk about that. And for a continuous variable, here, this is continuous, we must calculate a precise median. And then for mode, we just count the most frequent one, so we know for sure that's 8. But that's not really the middle score, is it? Again, it's a most frequent score, and that is one measure of central tendency, but that's not necessarily the center that you might think it is. But it is one measure of central tendency. For this one, again, the mode, there are 2 of them actually. It is either 2 or 8. Or 2 and 8. There are 2 modes. But neither of these scores are anywhere near the center. In fact, it's a symmetrical distribution, so the value would be somewhere near 5. Or actually would be 5, right down the middle. And you can calculate this as well with the mean and figure out what the median score as well. Here the median score in a continuous variable would be somewhere really, really interesting. So we'll talk about that as well. But for now, we'll start with, again, the mean. And before we do that, we'll talk about the central tendency measures a bit more. So here, looking at the free distributions, we can safely say that no single measure or no single concept of central tendency is best. Sometimes, for example, if we try to calculate the mean for all 3 of these, for distribution C, it won't even exist, or there's no score that is actually measured that has the value of the mean. So different distribution shapes would require a different measure of central tendency, or here a different conceptualization of what is considered to be center or the expected value. Again, distribution C, you can expect somebody to do really well or have a really low score, or somebody to have a really high score if it was between 1 and 9. And the middle score 5 didn't even happen at all. Nobody scored that. So again, different distribution shapes would have different measures of central tendency. So when we choose the best central tendency measure, we would need to look at the distribution in the data first, and then we make our choice depending on the situation. So when we do this, we need to know what the measures are first. So we'll start with the mean. You've probably done this at least once in your life or many times in your life and talked about this quite a lot. And being in a class, the average comes up a lot. What's the class average? What's your grade point average? And so on. So again, you can calculate the mean for population and you can calculate the mean for sample. And this is where our notations come in. Again, we use Greek letters for population parameters, like population mean. Here is mu. I can't write mu. M-U. This Greek letter mu. And so for this population size, we use big letter N, and I'm going to write P-O-P' for population. Notice the X value is the same because there's still participants. Okay, so this is a raw score, okay, from a participant. For samples, we have big letter M. You could also put X bar. That is also the same. This line here represents bars, so you can write X bar if you like. So if you're taking this course at Alexander College and using Canvas, or any college that uses Canvas, and you're doing a practice quiz and you're typing the answer for sample mean, you would type sample mean or X bar or M, or if you happen to know how to type the symbol X bar, type this, you can too. Okay. Notice here for the sample size, it's small letter N, and again the X is the same, representing the raw score. So the mean has 3 definitions, and each of these definitions help us, think about the mean in a more precise way. The first definition is sort of the math one that and knowing this definition would help you calculate the mean. First, you add up all the scores, and then you divide it by the number of scores. So this is where you get your sigma x over n, or, and this is for X bar or M. This is for sample. Or you get the population, which is sigma x over n, big N. Okay, so population, whoops, reverse that. Always double check the work. Sample, mean, population. Again, I'm using shorthand P-O-P'-N, mean. All right. So the first definition is sort of like the formula, but it's like the plain English way of saying it, so then you can explain to people or yourself how you get this value. Next definition is the amount each individual gets when you calculate the mean. Okay, so the second definition reads, let's say if we're supposed to distribute the scores fairly or equally here among everybody, how much would each person get? So let's say, for example, this is recorded at a time where we had COVID-19, and each of us, we are in a class of 34, and I include myself in this, so it's like 35. And there are, for example, 70 rolls of toilet paper. And so we got to figure out, how do we divide the toilet paper amongst 35 of us? Well, there's 70 rolls of toilet paper, and then there's 35 of us, so each person should get 2. And that's what we'd expect, right? If each person gets 2 rolls of toilet paper, we'll be like, yeah, that's fair. Everybody gets 2. If somebody gets 1 more or none or just 1 less, well, then it's no longer the expected value, so it's not fair or equal. So that's another way of defining the mean. And the last one here is going to be useful. The third definition is going to be useful when we look at the measures of central tendency, the mean, median, and mode, with the shape of the distribution. The mean as a central tendency measure is the balance point, is the pivot. And what that means is, if you have a distribution, let's say it's symmetrical, you put the mean, and the distribution itself is like a solid object. And you'll see this in the next slide. The mean here, be it population or sample mean, it's like the block or the pivot where you put on beneath the solid object, and the distribution as a solid object would balance. It would not move. The same can be said, for a skewed distribution. So let's say if the distribution was skewed, you'd move the mean, further or closer to the heaviest side, right? So then the distribution would stay in balance. So the pivot or the mean would no longer be in the middle, but it would move to the heavier side. So in a negatively skewed distribution where there's fewer scores on the left and more scores on the right, the mean would adjust. It would move. The math would move the mean closer, or closer to the heavier side or to the positive direction. Let me rephrase that. There's torque involved. You have a positively skewed distribution. Again, the mean would no longer be in the middle, like straight, like just the middle, because the scale would tip. And so the pivot or the mean would move again towards the heavier side, again towards the negative direction, but not all the way to the mode, and we'll talk about this. But it would move towards the negative direction, again as a balance. And one way to show you this is with the next slide. Here we have, let me count, 5 values. 1, 2, 3, 4, 5. I'll rewrite this, 4, 5. And so I could write this right here, like this, okay. I don't need a frequency distribution table for this. I just need the actual value. So I got 1, 2, and I'm ranking these. There are 2 6s and a 10, right? So there are 5 values, 5 x values. In this case, it's not symmetrical, but the mean, and we can calculate this. All right, so 1 plus 2 plus 6 plus 6. Okay, and then plus 10. So let's see what we would have here. 25. Sigma x equals 1 plus 2 plus 6 plus 6 plus 10. That's 25. And so the mean here is 25 divided by the number of scores, 5, and that's 5. So now we know one of these measures, and so here we got your mean. Here it happens to be the population, and so it balances in the middle. And one of the things we can do now is try and figure out what the mean for distributions B and C would be. So we got, if we rank our scores, so here we have 2. And before we do B and C, we can try with A as well. So we got 2, 3, 3, 4, 4, 4, 4 5s, 3 6s, 2 7s, and 1 8. So again, we are counting the X values as scores. So somebody scored 2, 2 people scored 3, 3 people scored 4, and so on. So there are a couple tricks to this that would help you speed up your calculations. I covered the 1 there. Let me try again. There you go. So again, if I were to go 9, 8, 7, 6, 5, 4, 3, 2, 1, and we did the frequency distribution earlier to 1, 0. So if you go your X value times your frequency, you can actually speed up your summation. So for example, 9 times 0 is 0, 8 times 1 is 8, 7 times 2 is 14, 6 times 3 is 18, 5 times 3 is 20, 4 times 3 is 12, 3 times 2 is 6, 2 times 1 is 2, 1 times 0 is 0. So instead of adding all of these up, like 2 plus 3 plus 4 plus 4 plus 4, although that's what you're supposed to do, all the way to 8, you can 8 plus 14 plus 18 plus 20 plus 12 and so on, plus 6 plus 2. Oh, I actually added all those. So if you wanted to do this quickly, okay, so here we got 20, that's 120, that's another 20, okay, that's another 20, so that's 60, and that's another 20, that's 80. So let me double check this. So 8 plus 14, that's 22, plus 18, that's 40, plus 20, that's 60, plus 12, that's 72, plus 6, that's 78, plus 2, that's 80. So we're good. So it is 80. So sigma x in the end, we calculated it, is 80. And so we divide by the number of scores. Again, there are a couple ways you can do this. With the frequency distribution, you can just count the f's, or the value of the f's actually, and add them up. So it's 1 plus 2 plus 3 plus 4 plus 2 plus 3 plus 2 plus 1. So that's 16. Okay. So again, 80 divided by 16. You can do long division with this if you need to. But let's say we do. Oh, okay. Is it 5? It is! Hey! 5 times 3 is 30. 5 times 1 plus 3. Oh yeah, that's 80. Perfect. So here we got the mean as 5. Done! Okay, now we're going to do the same for distributions B and C. So here we go. In this case, since we have a lot of individual scores, like 1, 2, 3, 4, 5, only one person scored in each, well, we can add those pretty quickly. 1 plus 2 plus 3 plus 4 plus 5, and if you know sigma notation, that's like 15. So that part's done. We can get that out of the way. But again, doing the full steps, we still can. So like 9, 8, 7, 6, 5, 4, 3, 2, 1. Again, 9 has 2, 8 has 4, 7 has 3, 6 has 2, and then the rest has this 1 in it, right? And so we can do x times f. Okay, 9 has 18. 9 times 4 is 32. 7 times 3 is 21. 6 times 2 is 12, and then it's 5, 4, 3, 2, 1. So I already know 1 plus 2 plus 3 plus 4 plus 5 is 15. So then I just need to add the rest of these. 15 plus 12 plus 21 plus 32. I wrote 33. 32 plus 18. Well, let's see. What do we have? Okay, we can do this left to right. So 15 plus 12. Okay, well that's 27 plus 21 plus 32 plus 18. And you've probably done this in, like, you can do this faster. For example, 32 plus 18 would be 50. So that's one shortcut you could do if you want. But I'm just going to go from left to right. 27 plus 21, that's 48, plus 32 plus 18. And then here, oh, okay, 48 plus 32, well, that's 80, plus 18. And then here you got 80 plus 18, well, that's 98. So sigma x here is 98. And so to calculate the mean of this, now let's pretend these are populations for now. Did I do population? I'll just use sample instead. There you go. 98. And this makes sense, right? You notice in distribution A, most people scored in the middle, like close to 5, and not many people scored, high. And there's nobody that scored 9. Whereas in distribution B, you got like 4 8s, 2 9s, 3 7s, and 2 6, and 3 7s. So you would expect the average to be higher, and you would expect there to have a higher, sum of x. So again, the same number of people is there, 16. So 98, 16. So again, we can do long division if we want to, if we have to. Okay. That'd be 3 or 8. No. One, 2, 3, 4, 5. 90. Nope. That's 80. Nope, that's not going to work. Aha. Alright. 6 times 6 is 36. 96. And okay, this is where it's going to get interesting. Let me double check my math first. 16 times 6. Okay. 6 times 6 is 36. 96. Okay. So, you got that going. 1, 16, 40. Okay. And then we got 2. And then, so 2 times 16, that's 32. And then that's 80. And that goes into 5. So, the mean for distribution B is 6.25. It can be X bar or M. Okay, so the last one. Notice so far though, the means are quite different. We got the mean for distribution A is 5, and the mean for distribution B is 6.25. So let's try this last one. The last one here, again, we can draw our frequency distribution. Okay, 9, 8, 7, 6, 5, 4, 3, 2, 1. And so there are 2 9s, 4 8s, 2 7s, 0, 0, 0 for 5, 6, 5, 4, 2 3s, 4 2s, and 2 1s. Again, we can save some time by multiplying your x's and f's. So 2 times 9 is 18, 8 times 4 is 32, 2 times 7 is 14, 0, 0, 0 for the next 3. Anything times 0 is 0. 3 times 2 is 6, 2 times 4 is, 2 times 4 is 8, and 1 times 2 is 2. So to add, then we add these up. We have sigma x here, 18 plus 32 plus 14 plus 6 plus 8 plus 2. So we can do this from left to right again. 50 plus 14 plus 6 plus 8 plus 2. Okay, that's 64 plus 6 plus 8 plus 2. That's 70 plus 8 plus 2. And can skip a step here. 80. 78 plus 2 is 80. So what's now we got to figure out the mean. We know the total. So the mean is 80 divided by n, which is 16. And we can do this again by long division if we want to. Well, we know the answer already. 5. So notice a few things. Yes, we definitely know by now, using the formulas, that we can calculate the mean for basically any distribution. And we notice that for each distribution, it has its own mean, even though the value for distribution A and distribution C in terms of mean value are the same. The difference, though, is that there is no score in distribution C that actually has the value of 5. Whereas in distribution A, there are 4 individuals that would have a score of 5, again within the real upper and lower limits. For distribution B, the mean is higher because there are more individuals that scored higher in the 7, 8, 9 range as well. So there you go. That's our means, and we've just calculated those. I'm going back here. And there. So we're on the 10th slide for now. And if you are doing the mean for more than one distribution, you can combine the sets of scores and follow the formula, and you can add up the total for one score and then add up the total for another score, or add up the total for another distribution, I should say. So you could, for example, do distribution A and distribution B, and then pretending that these are 2 separate distributions, so then you have 2 separate sets of samples, even though they're the same size, and then you'll get a combined or overall mean. So you can try that as well. You can try with distribution A and B, A and C, or B and C. So those are some options for you. Here is another table that you can practice with. So again, this is a separate distribution, and you see here the quiz scores are 10, 9, 8, 7, and 6 only. Doesn't know how this is the lowest score is 6, but you know, the distribution is as it is. And then there's 1 10, 2 9s, 4 8s, 0 7, so nobody scored 7, and 1 6. Again, you can do a column where you multiply the frequency scores or the count number of scores by the scores and the scores themselves. So this is 1 times 10. Here is 2 times 9. Here is 4 times 8. I can do these in brackets if you like. That works too. 0 times 7, pretty easy, 0. And 1 times 6. Then you would have your total score, and then you divide by your, and I'll cross this out here. And so, yeah, you have your sigma x, and then you divide by your n, and so you would have your mean. In this case is 8.25, 66 divided by 8 being 8.25. Just remove that right now. There you go. We'll do this. There you go. That works too. So again, sigma f of x, the same as sigma x, as we count all the scores. Okay, just do that one more time here. Like this. There you go. All right. So, learning checks. Question 1. A sample of n equals 12, so a sample size of 12, scores has a mean of 8. What is the sigma x value for this sample? I'm going to take a moment and do some calculations. It's kind of like the reverse process here for this one. So again, to calculate the mean, you have sigma x divided by n. In this case, is small n for sample, and you get the mean. So to get sigma x, when you know the sample size n and the mean 8, or m, then it's 12 times 8, which is 96. So now that we have calculated the mean, we can also look at the characteristics of the mean. And these characteristics can change when we start to change the distribution. So in this slide, we outline some ways that the mean can change. If we change the value of a given score, just one, that's going to change the mean. So for example, if we have 1, 2, and 3, and we find the mean of those 3 scores is 1 plus 2 plus 3 divided by 3, so that's 6 divided by 3, that's 2. If I just change one value, let's say I change the 3 to a 4, well, that's 1 plus 2 plus 4 plus, well, divided by 3, so that's 7 over 3. So already that's different. It's 2 1/3. That's no longer the same value. And it's because it's no longer the same value, it's no longer the same mean either. We can also change the mean by removing or adding a score. So in the same sample example we're using here, let's say I remove the 3 and just have 2. Well, 1 plus 2 divided by 3, 3. That would be wrong. It's 2 now. Again, when you remove or introduce a score, make sure you change the n as well. Okay, so here is now 3 over 2, which is 1.5. Conversely, if you add a new score, whatever it is, the sample size changes and the mean value can change too. So for example, I'll add another one. Let's say I'll add 4 now. So 1 plus 2 plus 3 plus 4 divided by 4. Well, that's 10 over 4. That's 2 1/4. Nope. My correction is 2.5. So again, a different mean happens when you add or remove a score. And when you add or remove a score, you also change n at the bottom as well. Another way you can change the mean is by changing each score by adding or subtracting a constant. So this could be like in a classroom example, if the classroom average was 50% and your instructor is, let's say, feeling generous and gave everybody a 10% bonus mark. Well, you can probably guess or calculate with arithmetic that, hey, if everybody gets 10% more, the average will move from 50% to 60%. Likewise, let's say, if in another class, the average was like, whoa, 80%. Ooh, okay. Hey, that was too easy. The instructor goes, maybe we move 10% of everybody's score. Well, minus 10 for everybody in terms of 10%. Well, that means the average will move from 80% to 70%. The same can be applied for multiplying and dividing each score by a constant. Notice though the key here is by each score in order to get a predictable mean value change. So you can try these yourselves with the different distributions that we've worked with to see the different ways the mean can change. So here's a picture example to show you how sensitive the mean can be. Remember, the mean itself in the distribution is the balance point or the pivot. And because you can change the mean by changing the distribution in a number of ways, whether you change one score or you add a score or subtract a score or take out a score or even add a score for everyone, or subtract from everybody, or multiply or divide from everybody, well, we can try this out. So there's 1, 2, 3, 4, 5 scores right here, and they are 3, and there's 2 6s, and then there's a 9, and then there's an 11. Okay, so right now So this would be 9 plus 6 plus 9 plus 11. And you can probably do this faster. I'm thinking 15 plus 20. That's like 35. But let's double check. Plus 9 plus 11. 24 plus 11. Yeah, it is indeed 35. So, yes, 35 divided by 5, because there are 5 scores, we counted, sigma x over n, is indeed 7. So, again, if we remove one of the scores, let's say 11, let's say this is gone, think for a moment, where would the pivot move at that point? Would it move to the right or move to the left? If you're thinking move to the left, you'll be right. Well, because let's say this is gone, and so there are more weights here now. It mean acting as a balance point. If the pivot doesn't move, the scale would fall over, would tip over. And so in order to balance the scale, the pivot must move to the left. And we can calculate exactly how much by, adding them. So we can go, we just figured out here, 3 plus 6 plus 6 plus 9, well, that's 15 plus 9, that's 24. We just calculated that. So 24 divided by 4, well, that's 6. So the pivot would now have to move here. If you add a score, depending on where you add it, let's say if it was 2, because there's one more here at 2, the pivot would also move to the left. And if you add one more to the right, the pivot would move one in the right side direction. If you shifted all the scores, like all these were to shift by 1, so now 3 becomes 4, the 2 6s would become 2 7s, the 9 becomes a 10, and the 11 becomes a 12. Well, naturally, you'd think, hey, everything shifted over 1, I better move the mean over 1 too. Likewise, you can move the mean over to the other direction if all the blocks were to move towards the left side. So that's how sensitive the mean can be. And the mean moves further when the scores change in a more extreme manner. So if you add more scores, the mean would change in one direction, the mean would move further in that direction. If you shift the scores further in one direction, it would also shift, the mean would also shift further in that direction as well. So that's when you get in the class pulling up the average. If you got somebody who scored 90% and the average is, 50. And another thing to consider is how many people are in the class. So if there are 2 people in the class and 2 people got 50% and somebody scored 90, that's going to be making a larger shift in the mean, for the mean in the right direction than a class of, let's say, 30 and the class average was 50, and then one person scored 90%. Yes, it would shift to the right, but it would be not as drastic because there are more people that are closer to the average. So a good mental picture and a good practice is a scale with the mean being its pivot. So here's another learning check. Question 2. A sample of 7, sample size 7, has a mean of 5. If all the scores were to double, what is the new mean? Take a moment. Again, you can either do this conceptually or make up some numbers and have it match to the mean of 5. You can have 7 5s, for example, if you wanted to, and then double those scores and see what you get. If you answered 10, double of 5, you're right. Again, we're following the concept of how the mean can change when the scores change. So that's it for our first part of chapter 2. We have covered the mean. And in the next part, we're going to do the median and the mode and how they would all relate to each other in a distribution. So again, the mean itself is pretty familiar to you since you've worked with it before. The median would be a bit newer if you haven't done any statistics in the past or ranked scores. But this is what we're going to do next. Again, there's no substitute for working in a textbook and taking your own notes and doing your own practice. But these videos should help you if you are a listening type of learner, you prefer to listen and watch. It should help you through the process and help you understand the concept and practice the questions with me as we do these questions. Again, if you got any questions, again, you can refer to the textbook that covers the thing in detail. You can watch the video in specific parts to catch what you missed, or you can email me directly and ask me the questions there. You can do this. We'll keep going, and we'll see you in the next one.